Okay, 17.7, Stokes' theorem. So this last couple of sections, Stokes' theorem and Gauss's divergence theorem, 17.8, are going to be our last two sections for the course. Just to give you the heads up, what are they? So remember Green's theorem? How number one, Green's theorem, as a bottom line, number one, it relates a line integral with a double integral over a planar region. What does that calculate? Well, let's recall the physics part of Green's theorem. Number one, depending on which version do you calculate, or which form rather, if you're calculating the curl form, that gives us the circulation, because it involves the curl, right? The two-dimensional curl. Or otherwise, number two, the flux version, that is using the two-dimensional divergence, that calculates the flux. Because again, these force fields, what do? Well, they're driving forces to move particles along curves, and calculate the work and all that, all that at this point. So, but again, those forces cause some motion. Cause some motion in the direction of motion of the curve, but also in the direction of the normal force. So we went through the details about this what's it called? These two projections of those forces. The one along the tangential, the one along the normal, etc. But what is Stokes' theorem? Well, Stokes' theorem is the first part of Green's theorem, that is the circulation, but in 3D, in space. Right? That's what it is about. So that's why I have the Green's theorem right here to recall what it is. Again, this is the two-dimensional, 2D curl, right? Or it is the z component of the curl in our curl calculation. But again, what is Stokes' theorem about? So in a similar way, we can calculate the work done into moving a particle along Z over a closed region R. However, instead, what if you turn this R, which is a planar region, into a solid, into a surface? So rather than calculating the work done along the curve, we'll be calculating, yes, the work done along the curve, but that's a curve that is in space, and the curve, it's a boundary in the surface. So that's very, very important, because, for instance, here, okay, let me go about GeoGebra real quick to show you how are we going to go about, how do we determine if the Stokes' theorem would be valid for a situation? Okay, well, it didn't go. Okay, so, and let me do the easiest. I'm going to turn off the lights real quick. So let me do a very basic case. So the case where we have a sphere, x squared plus y squared plus z squared equals to, let's do the sphere of radius 3, all right? So that's the sphere of radius 3. So of course, if you think about this sphere can be made of infinitely many level curves that together form the sphere. Some curves may be on the sphere, but some other level curves may not be on the sphere. For instance, let's see. Should I do? Okay. Did you guys help me here? Which curve, which circle would be on the sphere? So what circle would be a projection of the sphere, but in this case in the plane, on the xy plane? That is, we're going from 3D to 2D to help you out better. Okay. What does a sphere project? A circle. Radius what? Radius 3. Okay. In this case, I need the curve command, because okay, space in here. All right. So I need the curve in space, of course, and well, the z component will be 0. So 3 cosine t 3 sine t, and let me make this a 0, and the parameter in this case is t, and I'm just going to go between 0 and 2 pi. Oh, did you see how this curve, this circle, it's a boundary, it's on the surface? All right, okay. However, let me see if I can copy and paste. Yes, let me call this B. However, is that curve, this curve right here, 5? The circle of radius 5, is that curve on the sphere, on the surface? No. So that means that even though there is a driving force potentially helping move a particle in circles along that trajectory, Stokes' theorem wouldn't apply here because the curve right here, it's not on the circle of radius. I mean, it's not on the surface rather. All right. What about, okay, same curve. Let me do another curve. So how about let me call this letter C. Okay. Let me change the radius of that circle. Okay. So let me do 4. Let me do 4. No, wait, not 4. I was gonna do 2. I was gonna do 2. Okay, that's inside of the surface, so Stokes' theorem is not going to apply here. Let me change some coordinates. Let me give you another circle. Let me make the y component equal to 0, and instead, let me make this a 0, and so that's still a curve, but this curve involves the x and the z plane, but it's still on the boundary, right? So that means Stokes' theorem, it's still going to apply. All right. One more, and we call it a day. No, well, I mean at least for this. Now I need to delete this. Okay. And let me change this to, so A, B, C, we call this D, right? Curve D. Otherwise, it's not going to let me change. How about 7 and 6? So another curve that it's not a boundary of the surface, right? So in this situation, we wouldn't be able to use the Stokes' theorem. That's something we need to check before attempting to evaluate an integral related to Stokes' theorem. Because I mean, actually, the algebra is going to work, the calculations are going to work, but is it meaningful? How we're going to check that? Algebraically. Okay, you'll see about it. So let's go back to the notes. Okay. And again, this picture right here where we see the right-hand rule, so the orientation of the curve that it's a boundary on the surface is going to be oriented along with the surface. Again, for closed curves, we talk about this for a sphere, an ellipsoid, the orientation is going to be always outside unless we have an unbounded surface. The orientation needs to be stated otherwise, but typically we're going to work with closed surfaces. And we'll look at this vector pointing up. If you do the right-hand rule, it's going to go up. So that means the direction of the orientation is going to go along with our fingers closing our fist, right? So that is counterclockwise in this case, all right? And okay, how about we have a look at the definition theorem rather? Okay, so if S is an oriented surface in R3 with a piecewise smooth closed boundary C whose orientation is consistent with that of S, in accordance with the picture I just showed you, the right-hand rule and all that, let's assume F exists, right? F, which is given by Mn and B, that's the force field. It's a vector field whose component has continuous for all these conditions, right? It's differentiable at all points right here. Okay. Again, we're going back to evaluate line integrals because again, what does Green's theorem do? Evaluate a line integral, right, over a planar region. But now this planar region is going to become 3D, and that boundary over we're evaluating the line integral, it's on the surface. So instead, of evaluating this line integral, we will evaluate a surface integral. All right. So in a similar way that we use Green's theorem to evaluate a line integral using a double integral over a planar region, we're going to use Stokes' theorem as another tool to evaluate a line integral by means of a surface integral. That's why we have the ds, and well, that's why we discussed the surface integrals before. And well, you know, we already discussed the normal vector involved right here. That normal vector, that's what indicates the orientation of the surface. I'm not going to do the derivation of the gradient of the surface divided by its magnitude, so we already did that. We're just recalling this. So in the end, we will evaluate this line integral of f dr along the curve C by finding the dot product between the curl and the vector formed by negative g sub x comma negative g sub y, in a similar way we did with this, what's it called, the flux integrals. So guys, here is where I have my issues with the textbook. Number one, I replaced the F, G, and H of the force field from the textbook with M, N, and P with the notation the Larson textbook does to distinguish between the F and the G's, because do you see how there's another G over there? Sometimes it's tricky to distinguish which G is which. Is the G from the force field or is the G from the surface? And actually, I even changed this negative G sub x with negative Z sub x, negative Z sub y. Just because I think it's easier rather than using F and G's to not to confuse them with the ones from the force field. All right. Okay, so let's use the Stokes' theorem to evaluate this line integral of f dotted with dr along C with driving force 4y negative 2x5, where, well, what's the surface? First of all, the surface is the upper half of the sphere of radius 5. And well, C is the circle of radius 5. Well, I think in this case it's pretty clear that Stokes' theorem will apply, right? What do we have? Sphere of radius 5, circle of radius 5. We're good to go. All right. So, number one, oh shoot, we need to evaluate the curl. Let me write down the formula for the curl so we don't get back to the notes. Okay. So the curl of f, that is, rather than setting up the 3x3 matrix and find its determinant, use the result. That is, p with respect y minus n with respect z in the direction of I, minus the second component is negative p with respect x minus m with respect z in the direction of j plus n with respect x minus m with respect y in the direction of k. And well, I mean, we can find all these partial derivatives. Let's label m, n, and p, all right? So let's find the curl. So let's find the curl. Curl of f, that equals, okay, partial of p with respect to y, well, isn't that 0? Minus partial of m with respect to z, well, there's no z's, that's also 0 in the direction of I, minus, okay, parentheses, partial of p with respect x, oh, that's another 0, right? It's another 0, minus m with respect z, okay, there's not z, oh wait, it was n, anyway, n with respect to z, there were no c's, that's another 0 in the direction of j. And lastly, plus n with respect x, that is negative 2, minus m with respect y, that is 4 in the direction of k. That is going to give us, how about all zeros for I and j components and only negative 6 for the k component? That is coming back to component form, 0, 0, negative 6. All right, negative 6. What else do we need? Okay, so we need to take the partial. So I mean, what is the surface anyway? So we're given the surface in explicit form, right? That is x squared plus y squared plus z squared. So we need to get the surface in a way that we can find its partial derivatives. And well, in this case, I'm going to solve for z. So z squared equals to 25 minus x squared minus y squared, and z equals to the square root of 25 minus x squared minus y squared. And well, you might argue, did I forget to write the plus minus? Well, I mean, algebraically it makes sense to have those plus and minus. However, notice in the problem they're telling us the upper half of the surface. What's the upper half of the surface? Only the positive one, right? Only the positive radical. So that's why I'm neglecting the negative. So no, we didn't do a mistake in here. All we're going to do here is z equals to 25 minus x squared minus y squared to the 1/2. All right? And that's z. Okay, let's find the partials. So partial with respect x, that is 1/2 25 minus x squared minus y squared to the negative 1/2 times the derivative of the inside of the parentheses with respect x, which is negative 2x. All right, divide out the 2's. That is going to give us x over 25 minus x squared minus y squared to the 1/2. And you might want to come back to radical form. That is x over 25 minus x squared minus y squared. Well, hold on, radical. All right. So we needed a chain rule. It's also negative, by the way. Don't forget the minus. I forgot the minus. You guys don't forget it. All right. In a similar way, we can find the partial with respect to y. That is going to be a similar result, but negative y over the square root of 25 minus x squared minus y squared. Okay. So at this point, we have everything we need to evaluate this line integral. Using Stokes' theorem. Again, what are we calculating using the Stokes' theorem? We are, again, by evaluating a line integral. Evaluating a line integral that calculates the work done. Well, how do we know it's the work done by the driving force into moving a particle along the trajectory? See, well, that's because there's a force field involved, right? Otherwise, if we had a type 1 line integral, that's something else, right? Okay, so the line integral. So the line integral of f dotted with dr along the curve C, okay, that's equal to evaluating the double integral of the curl of f dotted with this vector here, that is negative z with respect x, comma, negative z with respect y, comma 1. And let me call this dA. All right? Hey, what happened here? So, dA. Okay. All right. What's the curl? The curl, which is this vector here, right? This, let me highlight this. Whoops. This is going to be our curl, and here we're going to have our partial derivatives with respect x, right? And our partial with respect y. That is our result there. Now, okay, what about the curl, first of all? So, yeah, the problem already looks hard, but actually, you'll see. So that's the double integral over the region R. Okay. The curl, what's the curl? The vector in green, 0, comma, 0, negative 6. Dotted with, okay, careful. That's calling for negative the partial derivative. But didn't we get negative signs for the partial derivative? Those negatives get killed. They become positives. That is x over the square root of 25 minus x squared minus y squared. -25 x squared minus y squared, comma 1. Okay. I need space again. Okay. There we go. dA. Okay, look at this dot product. 0 times this madness equals to 0. The second 0 times the other madness. That's another 0, right? What does that survive? -6 times 1? That's only a -6 surviving here. So that is the double integral over the region R. Don't worry, we will iterate in a second. So that is -6. Let me do 0 plus 0 minus 6 dA. Okay? 0 plus 0 minus 6. How about we take the -6 outside of the integral dA over the region R. Any ideas how to iterate or set up the double integral and evaluate it? What would you do at this point? Polar? Do we really need to do polar coordinates? Okay, polar. Okay, well, what would be the setting? Well, the limits, the bounds for polar coordinates if we were to do the polar coordinates? 0 to 5. 0 to 5. And then the angle 0 to pi. But do we really need the double integral? Okay, so, all right. So we are integrating over a circle of radius 5. Again, we did this before, right? What's a double integral with an invisible 1 in the integrand? Again. What is that? Area, right? The area of what? The area of the circle. Okay, what's the area of the circle? Radius 5. Don't even set up the double integral. Don't even set up. So this is going to be -6 times the area of circle with radius equals to 5. Come on, -6 times pi times 5 squared. Okay. So 5 squared, 25. 25 times -6, -150 pi. So that's our result. I mean, if you want to set up the double integral, do you want to review your polar coordinates? That's fine. But come on, just use geometry in this case. I mean, of course, in the case where the integrand is a 1. If we had like a variable x or y, oh, we're screwed. We'll have to go through the double integral, unfortunately. All right? Okay, what's next? Another one. Example number 2. Use Stokes' theorem to obtain the circulation if we let C be oriented, the oriented triangle line in the plane given by the equation 2x plus 2y plus z equals to 6 as shown in the picture here. And of course, in order for our circulation to occur, we need a driving force. What's the driving force? It's given by this vector field, this force field, all right? Well, I mean, I think it's clear that the boundary is on the plane, right? It's not outside like those examples I gave you where we have a circle on the boundary, another one inside the sphere, and then another one outside of the sphere. So no, in this case, I think it's clear. So we don't need to do anything algebraically. Oh, of course, in this case, they're specifying the orientation because if we think of a plane, the plane is not a closed surface, right? It's just a sheet. So in this case, we need to be specified about whether this the orientation is in this direction or inside of the screen in this case, okay? And well, since we have the orientation, look at this, the right-hand rule, look at the direction of my fingers, the fist is going to go in this direction. And guys, you know how to evaluate a line integral, right? With three different trajectories, parameterizing three lines. But we're not going to parameterize three lines anymore. Not anymore. We're going to use Stokes' theorem. Okay, but for this we need to find the curl. The curl of the vector field. So curl of f, which again I'm going to write the formula first. That's p with respect y minus n with respect z I minus, what's that? P with respect x minus m with respect z j plus n with respect x minus m with respect y k. Okay? Alright, so curl of f. P with respect y, okay. Again, let's label this is our m, n, and p. Alright? Okay, so partial of p with respect y. Well, there's only z's. So how about that's a 0? 0. Minus. Partial of n with respect, what's that? Z. That's xy. xy. So that's in the direction of I. Minus. What's that? Okay, the partial for direction. Alright. The curl about the y-axis. That is p sub x. So which is another 0 because there's no x's, minus m with respect z, that is 0 minus 1, that's minus negative 1, and careful with the signs in here, j, plus finally n with respect x, isn't that yz, minus m with respect y, that is minus 2 in the direction, let me make it look like a 2, there we go, in the direction of k. Let's clean this up. So 0 minus xy. Actually, I'm going to go back to component form. So the x component will be negative xy. The y component, careful because this is minus minus, which becomes a plus. So that's a plus 1 times the negative in the front. It's going to be a negative 1. So I'm going into like all the details here because oftentimes, especially when it comes to the second component of the curl, we tend to make a lot of sign mistakes because of all this minus here and there going on same time. So, okay, what else? Yz minus. This is a minus, not a times. Okay, so yz minus 2. All right. So that's the curl that we need in the integral. That's half of the setup. Number 2, we need the vector with the partial derivatives of the equation of the surface. Well, so number 1, we're given a surface. Let me go all the way here. So that'll be 2x plus 2y plus z equals to 6. I'm going to solve for z. Z equals to 6 minus 2x minus 2y. Let's take the partial. With respect x, that's negative 2. And with respect to y, that's negative 2 also, right? Negative 2. Okay, so we have everything pretty much that we need. However, when we evaluate this line integral, again, see the power of Stokes' theorem in a similar way we saw the power of Green's theorem. We no longer need to parameterize these three lines, right? Even though it's not the craziest thing in the world, we could do it, but it's not efficient. So we take advantage of this new tool, with these new theorems, and well, so we're going to integrate over a plane region. Well, what's that plane region? So actually it's labeled as R. And well, let me shade that region R. That's going to be this one, all right? So let's draw a Cartesian plane to look at that projection. So that'll be, do you see the intercepts there? 3 and 3. 1, 2, 3. 1, 2, 3. All right. So that'll be this region of integration. So y equals to 3 minus x. That's 0, that's 3, that's 3. That's r. Alright, let's shade. Let's keep shading this. So when we set up the double integral to find the total circulation, we will need to iterate using this planar region R. Alright? Okay, let's get ready here. Okay, do we have, oh yeah, we have everything we need. We have everything we need. So, the line integral. Notice the circle on the little circle on the integral, because that means we're integrating over a closed curve C of f dr that equals the double integral over the region R of the curl of f dotted with negative partial with respect x comma negative partial partial with respect y 1 dA. And again, dA, you know the drill. It depends on whether we consider this region as vertically simple or horizontally simple. Right? Let's go for it. So curl of f. Okay. Oh, this one is going to be an interesting one. This one is going to look big, I think. That is the double integral over the region R. We will iterate later. Don't worry about the limits for now. So let's do the vector operation. So the curl, which is negative xy, comma, negative 1, comma, yz minus 2. Dotted with the vector containing the partial derivatives. But again, those partial derivatives, we need to change the sign of whatever they are. Now, the partial derivatives of the equation of the surface, of the function that describes the surface, rather, they're already negative, right? Times those negatives in the formula, in the integrand, they're going to become positive. That is 2, 2, 1. dA, right? That's a dA. And what's next? Okay, so let's do this dot product right here. Interesting. Did you see anything interesting about this? Again, what's dA? What is dA going to be? Well, it's related to the area, not the area, but related to the area of the triangle, but I mean, it's either two choices. It's two choices. What are those two choices for dA? dy dx. Or? dx dy. But do you see a problem in the integrand? Yeah, we have a z right there, right? We have this z hunting here, so we don't want that z. We need to get rid of z, right? How? Well, you're given, you already wrote an explicit function for z in terms of x and y. So let's substitute that there. And okay, that'll be, okay, am I gonna have enough space? No, I don't think so. The double integral over the region R. Everything else remains the same. X of y, comma, negative 1, comma, y times z. Careful, that's 6 minus 2x minus 2y. Minus 2. Close the vector. Dot it with 2, 2, 1. dA. We will iterate later. We will iterate this later. Okay. Yes, we will have to distribute the y, combine like terms if applicable. We'll see about it in a second. Okay, so this will be the double integral over the region R over negative x of y, negative 1, 6y minus 2xy minus 2y squared minus 2. Oh, nothing to simplify any further. Dotted with 2, 2, 1. dA. Okay, so dot product. All right, dot product. Okay, let me use different colors to show the dot product, because we have like a lot of quantities here, right? Okay, so negative xy times 2. All right, that's how we're going to do the first component, the x components with the x components. Negative 1 times 2. And lastly, we use a different color, maybe this blue. Okay, all this madness here this garbage here times 1. Alright? Okay, let's dot product that. So, negative xy times 2, that's number 1. The integral over the region R. Parentheses, no more vector notation because again, the dot product between two vectors is a scalar, okay? So, negative 2xy, negative 1 times 2, that's minus 2. And all this 6y minus 2xy minus 2y squared to minus 2, all right, dA. And do we have any like terms? Yes, I believe so. Those like terms are going to be the negative 2xy's and what else? The negative 2's. Use purple. Oh wait, hold on. Just these 2's. Alright. Let's simplify the integrand. That is the double integral. I will iterate at this point. So number 1, negative 4xy plus 6y minus 2y squared minus 4. I'm going to go dy dx because we already have functions of x in our triangular region that we described at the top of the page. What else? So, and we're going to take this as vertically simple region. And well, let me go back to the top a little bit. So, top minus bottom, the top which is the diagonal line, the bottom which is y equals to 0. So that means it's going to go between 0 and 3 minus x. And the limits in the direction of x are going to go from 0 to 3. And I don't want to evaluate this integral. I mean, it's polynomials, can take forever. You guys are experts in integration, right? So we're going to get negative 18. Alright? Alright, so that's another Stokes' theorem example.